Right. Now that we have finished defining the functions that will be needed in training and diagnosing our model, I like to write the main loop where the training actually happens, and within that, wherever we use the validation functions to see what is actually going on. So before I embark upon that, let me define certain quantities I need. First, the number of epochs that I'll be training for. So let this be 200 for now. Secondly, because I'll be doing a batch wise training, I like to know how many batches there are. So n underscore batches is n underscore images right. So we've not defined n underscore images yet, so I'll use the train underscore set dot shape 0 divided by mini batch size. Now the number of training patches might not be equal to a perfect multiple of the mini batch size. So in that case, I'll need to increment the mini batch size by 1 so that all of my data is used for training. So if check its remainder with respect to mini batch size is not equal to 0, then mini batch size should be incremented by 1. Right. So let's write the two loops for epoch in range and epochs. Within that, for batch in range in batches, call the train underscore fn of batch. Now train fn takes another argument, that is the learning rate, which is a tensor variable, and I kept it as a tensor variable because I'd like to modify it later on in my training. Maybe not in one of these early tutorials, but later on. So let's keep a scalar value lr underscore for the learning rate, which I'll pass to train underscore fn. This outputs a cost. Now because we are doing a batch wise training, let me call it a batch cost. I like to aggregate these batch costs into an epoch cost, that is take the mean of all the batch costs. So let me first define an epoch cost equal to 0. So at the end of every training batch, epoch cost gets incremented by as much as the batch cost, and finally in the outer loop, epoch cost gets divided by the number of batches. Now again, if the number of training examples is not a perfect multiple of the mini batch size, this formula is not fully valid. Alright, our next step will be to use the validation functions that we defined above. So for that, I like to use the validation set only at certain intervals. I wouldn't want to do it every epoch because it's time consuming. So I'll have a validation frequency at which I'll be doing this. So I'll use them at every 5 epochs. So I'll check if epoch plus 1's remainder with the validation frequency is 0, because otherwise I'll be saving the 0th epoch as well. Not very useful. So a validation cost should be equal to validation function, and reconstruction should be equal to reconstruction of validation. Apart from this, now as I said, I'll be using the reconstruction to have a powerful visual diagnosis of how well the system is doing. So to compare, I should also save the original validation images which are being reconstructed. So if the epoch is 0, get the original images as valid underscore till n samples. Now I have these originals and the reconstructions in the form of row vectors. So how do I convert these n samples, that is 400 row vectors, into images? For this, I'll be using a function called tile raster images. This is originally from the Lisa Lab deep learning tutorials, but I modified it a bit so that it can also show four tensors. We'll be seeing these when we work with convolutional networks, and I added it to the custom IO module. So actually we didn't need this import custom IO statement at all. So we'll do from custom IO dot utils import tile raster images as show row vectors. I always use this other name for tile raster images to remind myself that the purpose here is to actually show row vectors. The spelling is wrong here. So to use this, I'll write, so this outputs an image when you give it a set of row vectors. So out or image of original is show underscore row vectors, and what you give it is the original. Apart from this, you pass some parameters which are tile shape, tile spacing, and the image shape. So if you pass it a set of row vectors, what show row vectors will do, that is what tile raster images will do, it will create a grid based view based on your tile shape. So for example, what I'll want to do is I'll want to give it these 400 row vectors, and I'll want to display them in a 20 cross 20 grid. That is, these 400 vectors will be arranged in that way. So this is what the tile shape parameter specifies. So I'll define an x underscore tile underscore shape as, now I might want to change my number of samples in the future, so I'll define a function over those. So square root an integer of this n samples, and so if you multiply these two numbers together, you'll find that it is more than the number of samples, but it's an easy way to get the tile shape, so I prefer to use it. So we can put x underscore tile underscore shape here. Now tile spacing specifies that within this grid, between two elements, that is within two samples, how much of a spacing do I want, that is vertically as well as horizontally. So I might want to put it as 2, 2. Then image shape is just the shape of the constituent elements of this grid. That is, all the row vectors have to be reconstructed into a 16 cross 16 image, right? So image shape can just be the patch size. I hope the function of show vectors is clear now. Now once I have this output image, that is image underscore original, I'll want to save it. For that, I'll use another function from the custom IO module. That is imsave2. This is just a wrapper over skimages imsave function, which I think is in skimage.io. Yeah, it's in the skimage.io module. So what imsave2 does, apart from imsave is that you pass it a path that might include directories not yet there on the disk, and it will create them on the fly. So I'll use imsave2. Now for the save path, I'll define a base directory within which all this data is going to be saved in a structured form. So save underscore dir, let's call it an AE underscore tutorial, and I'll define a reconstruction directory using this as os.path.join save underscore dir away, comma, recons. So for the original images, I'll want to save it as a path.join of the reconstruction directory and the image name, which will just be original.png, and then I pass to it the image created by show row vectors, and it just saves it. So I'll use the same scheme for the recons array created by reconstruct validation. So image underscore recons will be the show row vectors of recons. Everything else remains the same. We don't need to define the reconstruction directory again. I will save it in the reconstruction directory, but with the name as the epoch in which we have reconstructed this. So let me add epoch here, and what we'll be saving is img underscore recons. Apart from seeing the reconstructions, another powerful visualization is to see the forms of the filters itself. Now if you remember, while making the upward pass, we were taking the dot product between the weight matrix and the input image. That is a dot product between each weight in the W matrix, not each weight actually, each hidden unit's weight vector and the input image. So the weight vector has the same dimensions as the input image, and in fact we can say it lies in the visual space, that is, it can be seen as an image. So we'll want to do that here. Let w underscore be the current value of w. Now w is a shared variable, that is, it's an object, and to access its data we have to use the get underscore value function of it. So we save this value in w underscore, then we make an image out of it as show row vectors of w underscore tile shape, tile spacing, and image shape. Now the image shape remains the same as for the reconstructed and the original images. So image shape becomes patch size. Tile spacing 2,2 is a good number, so I'll want to retain that. Tile shape is different because the number of weight vectors is different from the number of samples. So let me define a W tile shape as well. So we can call it an integer of np.sqrt of nhid, and similar to above, the second dimension will just be this with a 1 added. Alright, so we can put W tile shape here, and we have the image of W. We'll save this using imsave2. So the directory for this will be the save dir. The directory for W images will be the filters directory, and we'll again give the image the name we'll give the W image the name as the epoch. So it is e.png, and what we are saving is img underscore w underscore. Alright. So I have not yet used the training and the validation cost that I have been saving. What I like to do is to graph their progress and see how they decrease as my autoencoder is learned. Another thing to see over there is how well the validation error follows or decreases with the train error. If we find that the validation error has stopped decreasing or is increasing while the training error continues to decrease, it's a sign of overfitting. So again, the error plots are a useful thing, useful diagnostic uh, that we have. So for that, before I do that, I like to import two more functions. So first, from custom io dot imsave2 import save fig2. This is again a wrapper for the savefig function found within matplotlib, and it adds the same facility as imsave2 by creating directories on the fly. And from custom io dot utils import plot together. Plot together is a wrapper for the plot command found in matplotlib, and what it does is it takes pairs of pairs of x and functions of that x, that is xy points, and plots them together on a single graph. I'll show you the usage that will make it clearer. So I'd like to create a list which will keep accumulating these costs as we train. So cost underscore train so far, and cost underscore validation so far. I like to visualize these graphs every time I validate my model, so it will come within this if statement on the inside. So cost train so far becomes appended with the epoch cost for this epoch. Cost underscore validation so far becomes appended with the validation cost for this epoch, and number of x points will just be a range over the length of cost train so far. We could have taken cost validation so far as well. Both of them will be of the same length. So we'll use plot together as you pass it a list of tuples. Each tuple contains the x coordinates as the first member, so that will be n underscore x underscore points. Actually, it shouldn't be n, it's not a number. These are the x points, x underscore points. The second one is a function over these x coordinates. So we'll want to see the training cost versus the x points, and cost validation so far. Alright, then to give each of these names, legends will be train and validation. We'll want to save it in F. Now plot together makes a figure and keeps it hidden and returns to you a figure handle. And now you can use save fig2. to just save the matter in this figure to a file on disk. os.path.join of save directory. Then within that we'll want to save these in an error plots directory, and the image names will just be the epochs where they were taken. Epoch dot png. So with this we can now see the error plots at every 5 epochs. As the training is proceeding, we'd also like to see how far along we are. So print epoch. So I just ran it in the background to see what errors there are. So first, here in the train fn there are 2 commas. Secondly, here I used custom underscore io dot imsave. It should have been imsave 2. And most importantly, I use row vectors on the reconstructions for the validation set, but I forgot that the reconstructions were in the form of column vectors. So I should be taking a transpose of this here, and with that it's ready to run.